The title of his presentation is Adhesion of Polymers to Diazonium-Modified Surfaces. Please, Mohamed, it's a pleasure to attend your lecture.
Thank you very much. Good morning, everyone. Thank you very much, Professor Elisabetta Ranucci. Dear Elisabetta, it's a great pleasure to speak live from Calvados, from the Normandy sea coast in France, about adhesion of polymers to diazonium-modified surfaces. Actually, I come from the surface analysis area, and serving other colleagues understanding the chemistry of their surface chemistry pushed me towards the design of new coatings and investigating the fantastic surface chemistry of diazonium salts, which are very well known for organic chemists. So this is the outline. I will briefly speak about the coupling agent for polymer adhesion, and then I switch to the salient feature of diazonium salts. Then I will select some methods of grafting polymer coatings from the research of my group. I will show some application and then some future developments, and I will come to the conclusion. Okay, so most of you, I've seen a lot of slides yesterday about polymer adhesion and the induced mechanical properties of composite materials. Most of you know organosilanes used to modify metals, ceramics, clays prior to adhesion via covalent bonding of polymers, or the growth of polymers by grafting from methods. Thiols are known to modify gold and platinum, and ammonium salts or ionic liquids are known to intercalate clays and make clay polymer nanocomposites. For carbon nanotube and graphene, much has been done with pyrene, modified pyrene with some functional groups, but our racehorse is the diazonium salts, which were discovered in the 19th century by Peter Gries. He coated them diazonium because diazo comes from the French diazote, 2 nitrogen atoms. He didn't know how to call these compounds, and they have made the very long happy days for the organic chemist, because you can make so many series of compounds with diazonium salts until 1992, when my former professor at the University of Paris, he understood how diazonium salts react with the surfaces via a radical attack of the surface, and he worked on carbon, and it was the right example to study a radical attack on carbon. So since then, much has been done to modify. From understanding how it works at the surface, it became really a process of surface modification. So we thought, why not try, and if aromatic amines are available commercially, so several of them are available commercially, we thought that we should go to polymer grafting, given my interest in polymers in general. Okay, so diazonium salts in organic chemistry are known for the synthesis of several compounds, like for example pH indicator methyl orange, and for surface chemistry we tried so many aromatic amines which we used to synthesize the diazonium salts. I underlined some which are important for click chemistry, for example, for ATRP, surface-initiated ATRP, or radical photopolymerization, or photoinverter, or oxidative polymerization of pyrrole and aniline. There are also other important diazonium salts which were synthesized by many groups, like diazotized epoxy, diazotized oligomers, calixarene, diazotized C fibers, carbon nanotubes, silica nanoparticles, and so on. And the very first book on the surface chemistry of diazonium salts was edited by me in 2012, and I received contributions from several groups, including mine. Okay, so most of you know that diazonium chloride are explosive, and it's better to prepare tetrafluoroborate, which can be kept in fridge, but stable at room temperature are the tosylate and the triflate diazonium salts. The triflate, according to a Russian group from Tomsk Polytechnic University, by calculation, the theoretical computational chemistry, they are stable up to 80 years. And these are, for me, probably the most important ones. They are stable at room temperature, tetrachloroorate, diazonium tetrachloroorate, because when you reduce these diazonium salt, both the diazonium and the tetrachloroorate reduce. So this is reduced to gold nanoparticles, and it is capped by aryl groups. So these are important to make in one step. There is we make aryl capped gold nanoparticles. So the reduction of the to make the reaction at the surface, we can use, of course, the spontaneous reaction if the surface is sufficiently has a reducing power towards the diazonium salts. Also, we can use other reducing agents like iron powder or vitamin C by electrochemistry, photochemistry, and many other processes. Spontaneously on copper, for example, we have demonstrated that gold, diazonium gold tetrachloroorate react with the surface of copper, and to visualize here, to permit the visualization of latent fingerprints on copper. This is for forensic science. This has been published recently in early 2020 in Langmuir. Okay, so the like silane, the diazonium salts, they react with so many surfaces, practically all surfaces: carbon, semiconductors, metal, polymers, insulating materials, like, for example, cellulosic materials, but with different mechanism. Either you isolate the salt, you make the salt if it is stable and not hazardous, or in situ generate the diazonium salt from the precursor aromatic amine. It can go to oligomerization with some azo links within the layer, or some azo links at the interface. By XPS, we have demonstrated the existence of carbide at the interface with metal. Other groups from the South Paris, they have demonstrated the bond between gold and diazonium salt without deazonization of the salt, without removal of the N2. This can be proved by XPS. We can see the nitride here. By Raman, a group from Canada has demonstrated the existence of carbon gold at the interface by Raman spectroscopy, by CERS, and by TOF-SIMS, time of flight secondary ion mass spectroscopy. This is a very, very powerful surface analysis technique. We can demonstrate the existence of carbon-carbon bond with glassy carbon or COC bonds, and also the oligomerization of the aryl groups at the surface. Also on aluminium, we can have the aluminium carbon bond or aluminium LaOC bond at the interface. With my group, we have demonstrated that there is a very immediate, instantaneous reaction of intercalation of clays with diazonium salts. For example, soda clay, the sodium is stripped from the clay, and it is replaced by the diazonium. If we heat up a little bit, we can make the reaction. We have a diazo-ether group, which is not very stable. So if we heat up a little bit, we can end up with aluminosilicate carbon bond at the interface. And from that, we have done some photopolymerization to make a clay polyglycidyl methacrylate nanocomposites, which could be used as a filler, actually, with a reactive filler, because here you have a lot of epoxy groups borne by the lamella of the clay, and this could be used for, so as I said, as a reactive nanocomposite filler. So by computational chemistry, it has been also demonstrated that there is interfacial covalent bonds, carbon, oxygen, iron, or directly the carbon iron bond. And this has given credit to our work by XPS in 2003, when we demonstrated the existence by XPS of carbon iron bond. So this give full credit to our work back in 2003, because there was it was controversial, and some people didn't believe of the existence of carbon iron bond, although we have shown that by XPS. By DFT, now it is proved that the calculation proved that this is the work of Jiang in United States. They proved very strong adhesion bonding between the aryl groups and the carbon, and they have done that on carbon, on graphene-like sheets, but also on metal surfaces. So because the aryl surface bonding is very strong, this led to a lot of developments, industrial developments, and the most known of them are the diazonium-modified carbon beads for inkjet inks produced by Cabot a long time ago in United States. And actually Cabot has collaborated with Chris Matiaszewski to prepare carbon polymer nanocomposites, but using the diazonium salt as a compound to provide a surface initiator of ATRP. Sinomed has exploited the patent by Christophe Bureau and Jean Pinson, and now they produce stents with modified with diazonium salts and a coating for drug eluting stents. Turbobeats in Switzerland, they produce magnetic nanoparticles for biomedical applications. They cap the magnetic nanoparticles with this very small carbon layer, because the carbon layer reacts spontaneously with diazonium salts and can provide a functionalized aryl capped magnetic nanoparticles. In Belgium, X4C, they are very well known for the production of calixarene with 4 diazonium salt functional groups for the production of arylated surfaces or even gold nanoparticles. Concerning my research with my group, we have done a lot of work on surface-initiated ATRP. We use diazonium salt to graft initiator of radical polymerization or other types of polymerization. We have done click chemistry as well. surface-initiated radical photopolymerization. Some of my group, Claire Mongenet, has done a lot of photo-ini further. Now she moved to another university in central Paris. Click polymerization. Recently, we have done this in my group, and condensation polymerization, and finally, electropolymerization of conjugated monomers like pyrrole and aniline. The application encompass antibacterial surfaces, electrochemical sensors, composite catalysts, reactive fillers, and so on. So I'm going to, I selected the examples. I finished my slides yesterday because I had to look at this some lectures, and I selected according to what has been said yesterday. I added some slides. For example, first lecture yesterday by Professor Diaz was about click chemistry. We wanted to investigate this area. We using carbon nanotubes with diazonium salts. We started with we fabricated the diazonium salts of the this aromatic amine, so we can modify easily the carbon nanotube with this diazonium salts in isoamyl nitrite. So we diazotize in situ in the presence of the carbon nanotube. We have this this hybrids, nanohybrids, clickable nanohybrids, and we have done the polytriazole using these two monomers which were prepared in the laboratory. So we ended up with polytriazole, in situ generated polytriazole on carbon and nanotubes. It could be, we didn't try to find some applications. We published this in a small paper in 2016. I just want to show you the XPS part. This is the contribution of the carbon nanotube, and if you see here the different contribution of these functional groups, the ethylene glycol part, which we see here, the CN bonds from the triazole, and from this part of the polymer chain. So we, of course, we have used also Raman Raman spectroscopy to determine the D to G ratio, which was shown to change upon the grafting of the diazonium and the polymer. Very short. This I was not. I didn't expect I didn't plan to show this, but because we talked about click chemistry yesterday, we have made alkanelated carbon nanotubes. We prepared by ATRP an azide terminated polymer, which we clicked on the surface. We used it for, it's from polyglycidyl methacrylate. We opened the epoxy here, and then we attached we immobilized palladium salt, and which we reduced in situ for to make a nanocomposite with immobilized palladium nanoparticles for Suzuki CC coupling reaction. We have done also the same on with using gold nanoparticles, and here we have made this with polyphenylpyridine, and we found that the nanotube modified with polyphenylpyridine is pH responsive, as we demonstrated by XPS. But we didn't go any further with this part of the work. Second example, besides the click chemistry, is the preparation of fillers. We have modified in a collaboration with Poznan Technical University in the west of Poland. We worked on the modification of silica and zeolite for abrasive tool. This is the abrasive tool here, and we were interested in this part of the tool here, the novolacant filler, and the filler was either zeolite or silica. So, for example, for the zeolite, we have investigated, for example, the steric effect. How could it work when we have the reactive group, which is of interest, is in either para position or ortho or meta position. So we have done both kinds of modified filler, and we see that there is a steric effect when the functional group of interest is near the diazonium salt, because the modification of the zeolite is occurs, but at a lesser extent when we have the functional group in ortho position compared to para position, where we have here excess of aryl groups at the surface of the zeolite particles. I think it's called, this is kind of condensation reaction with Novolac, and we have compared the reaction of Novolac with the modified zeolite or silica as well. For example, we when we make the resin with Novolac filled with modified zeolite, and we tilt this the plane here, we see that if there is no interaction or weak interaction or between the zeolite, modified zeolite, and the Novolac, there is a complete flow down of the resin, of the modified or the filled resin. But with the para position here, we have strong interaction between the Novolac and the modified zeolite, and we have only a small distance on which the resin is flowing, because start of the we have a start of a cross-linking of the resin used to make the abrasive tool. For flexural strength, we demonstrated that we have better mechanical properties for the para position compared to the meta position modification of the zeolite, and before it's used as filler for the resin. And here we have the heating, the cure at higher temperature. We have even better mechanical properties, better flexural strength. So these reactive fillers are really important, and we can tune the mechanical properties with the taken advantage of the para position of the functional group CH2OH in para position compared to meta position, but also the extent, the concentration of the modification, the concentration of the modified fillers, and the temperature of cure. I still have 10 minutes, 15 minutes. In association with Mahatma Gandhi University in south of India, we have done, we worked on polyaniline clay nanocomposites. They are fillers for epoxy. We intercalated the clay layered silicate with this diazonium salt, which is used to start the oxidative polymerization of aniline. Intercalation was very quick. Curing at 60 degrees ensured the covalent bonding of the aryl group to the clay lamella, and in this way we obtained some exfoliated clay polyaniline nano composite. And here we can see that there is a loss of the some important diffraction peak from the clay, which shows that there is exfoliation or high intercalation of the clay with polyaniline. Two things may happen. Either when we use the diazonium salt, we intercalate the clay, we make clay polymer nanocomposites with some percolation here, and we obtain a high conductivity, electrical conductivity, 5 orders of magnitude, much higher than the clay polyaniline nanocomposite without any pre-intercalation with the diazonium salt. So the diazonium salt here permit not only to intercalate the clay, but to make a conductive path here of the polyaniline in the clay polyaniline network. Interestingly here, when we see the fracture surface of the composites, epoxy, this is the epoxy and the fracture surface. We monitored also the extent of diazonium salt, sorry, of the mass loading of the filler in the epoxy, and we can distinguish between the nanocomposites when it is epoxy nanocomposites prepared in the absence of diazonium salts, and in the presence of diazonium salts used to make exfoliated clay polyaniline nanofiller. Here we have a brittle failure, almost the same as if epoxy was not filled with the filler. And here we have a ductile failure, which is a sign of a very strong adhesion between the nanofiller and the epoxy. If we look at the interface here, we have the intercalation of the clay with the diazonium, the fabrication of the polyaniline. We can also, the polyaniline can serve to react with epoxy. We have the crosslinker of the epoxy resin here, and we can see this is a schematic view. This is what we propose as a mechanism to make a cross-linked epoxy using the crosslinker and also the nanocomposite filler. Okay, I'm going to, I think I will, this is the last important study. Recently in association with University of Dakar in Senegal, we worked on the development of sensors for electrochemical sensors for environmental application for the detection of heavy metal ions. This is not covalent bonding of the polymer to diazonium-modified surfaces, but most probably strong electrostatic interactions. We worked on flexible ITO indium tin oxide electrodes. They are coated on PEN foils, maybe 200, 300 nanometer of ITO coated on the substrate. They are sold as A4 sheets. You can cut to the size you want. We have worked on diazonium modification and the electropolymerization of pyrrole. You can see here by electrochemistry that when we graft the diazonium salt of this phenyl diamine molecule, you can see here after several cycles that there's a passivation of the ITO. So if the aryl layer is very thick, the electrode becomes passivated and insulated, and there is no more electropolymerization. So we have tuned the time for grafting the aryl group from the diazonium salts. You can see here for 15 seconds or 30 seconds, we can have the polymer fabricated by electrochemistry. But if the aryl layer is very thick, this is not possible because the electrode becomes insulating. We have monitored, of course, the change in the, we have scanned the surface here from the bare naked ITO to the aryl layer and then the polypyrrole by XPS to check the uniformity of the deposited polypyrrole layer. For example, in XPS, when we start the vacuum, if there is no adhesive layer from diazonium salts, the polypyrrole film is simply delaminated. It is sucked by the vacuum, but here it is very stable, and we can see the interface under the CCD camera of the apparatus. I don't have time to show this. Maybe
you have still, I mean, there are 7 minutes left, so
okay,
please,
okay.
You can proceed. Thank you.
Okay, so this is only 1 minute video showing the adhesion of polypyrrole to unmodified and modified ITO, flexible ITO. This is on flexible ITO, bare flexible ITO. You see, by washing, we can remove very easily the conductive polymer. And of course, some people in other conference, they asked me if there is a TPL test to measure adhesion. Oh, sorry. Oh. Okay, so you see that the adhesion is only, we could remove the film on diazonium-modified electrode only by scratching, not no other ways. The adhesion was very, very strong. We made some electrochemical sensors. We tuned the adhesive layer for polypyrrole with the time of electroreduction of the diazonium salts, and we made some sensors which are very sensitive. We reached the nanomolar detection of lead. We studied the selective recognition of lead with cadmium and copper. But when we mix all together the metal ions in the same wastewater medium, we can have some competition. We improved the selectivity and recovery of lead using polypyrrole and this derivative of EDTA as a chelatant for the metal ion. And you see here, even though we go to 40 times copper ratio of copper 2 to lead 2, the recovery is very good for lead with this skeleton used in association, in combination with polypyrrole. By DFT, we have shown that the stability of the complex polypyrrole EGTA lead complex was stronger because the EGTA is hexa-coordinated with lead compared to the penta-coordination with copper. I'm going. We talked about polyaniline yesterday.
Sorry, Mohamed, can you hear me?
Yes.
You have 3 minutes left.
5 minutes.
3.
3 minutes, okay.
Okay.
So what is next? Maybe with diazonium salts, explore very much the mixed array layer, make more hierarchical micro nano reinforcement for polymers, like for example here a Chinese group who worked on carbon fiber but grafted with carbon nanotubes via the diazonium salts. Also, the scaling up the modification of larger sheets of polymers or surfaces or carbon textile or whatever. So scaling up instead of working on small samples, and also now investigate or combine iodonium and diazonium salts. There is a lot of work now done on similar onium salt, like iodonium salt, for the surface modification of carbon materials and other surfaces. So for the take-home message is, as most of you know, interfacial chemical engineering is a key parameter towards the fabrication of robust and long durable system. Diazonium salts are really excellent new surface modifier and coupling agent for polymers. Also, they are more hydrophobic than silane. So the interface in composites, the interface can withstand humidity and water attack of the interface. The stereochemistry is very important, as I have shown in some of the examples. And really what has been done in these 30 years, for sure it will continue to draw attention of other groups on the importance of diazonium salts in surface science and in polymer science in particular. And for me, really, to be frank, having worked on diazonium salts for 15, 20 years, I really believe, yesterday somebody said about the new kind of ITRP as really as an important method of polymerization for the future, somebody from Poland. I think also as silane were the coupling agent for the 20th century, so diazonium salts are coupling agent mark in the 21st century. With this, I would like to thank you very much for your kind attention. This is a picture from the seaside behind me here, 2-3 minutes walk from my vacation place, and it has been a very great pleasure to interacting with you from Calvados, from the Normandy coast. Thank you very much.
Thank you very much, intern Mohamed, for your very interesting presentation. Now the session is open for discussion. I'm watching the chat and no questions are available from the audience. So maybe Paolo, you would like to make a question?
Yes, just a short curiosity. The curiosity is about the coating of metals, because I understand that you can coat metals with your techniques.
Yes.
But in case of very electropositive metals, these metals are covered usually with a layer of oxide that protects from further corrosion. Should you remove the oxide layer, or they can react, or even they help in adhesion?
This question was important a few years ago, but now most of authors who tested the adhesion on metals, they know that there are other mechanisms of interaction of bonding, and the mechanism it yields metal oxygen carbon interfacial bond.
I see.
This is for sure.
So oxide has a place.
Even on oxides it works, because we have done also a lot of work on silicon dioxide, on silica actually, but also on aluminium, for example, for propellants. Aluminium nanoparticles are used, and it was demonstrated. That's what I have shown in one of the slides. There is the existence of Al aluminium OC interfacial bonds. So I think most probably, of course, what is important is that the metal, with or without the metal oxide layer, it must be very clean. If it is not clean, it does not work.
Of course, yes.
Okay. And now,
thank you very much.
Thank you, Paolo. A question from Nate Asme, that is a young scientist working in Luxembourg. And the question is regards the scaling up of this process, especially when oral salts are required. So is the scaling up feasible? This is the question.
Because of the dangerous, the scaling up, in which case?
Orate salt is necessary, then in this specific case, is the process scalable?
With the salt, with diazonium salt?
Yes, but I mean when the counter ion is a gold salt.
Actually, we tried on, for example, for copper, we tried on small sheets, but we didn't go. It was a very short-term work. We worked on coins, on Eurocents coins, and also on old French francs coins. It's the biggest we have done, but for sure, if we go to 5 centimeters square or diameter or more, I think it will be possible. But the biggest we have done is 5 centimeter on a copper sheet, and a few cents, 1 to 5 cents of euro. It's maximum was 1 centimeter.
Sorry if I interrupt you. I understand that Nave was meaning especially regarding the costs of the process. But I think that it is a piece of discussion that can be continued further. There are so many questions that could be asked regarding this very wide and versatile approach. And I personally will be happy to continue the discussion afterwards if you are available.
Yes, but it is done industrially by Cabot, so I don't think there is a price issue, a very big price issue. Thank you.
Thank you
very much.
Thank you,